Okay, so in this video, we're going to talk about logic gates as it relates to neural networks. I'm first going to talk about neural logic gates. All right. So I have this little demonstration here. This is computer engineering for babies. I love this. I think this is really cool because as someone who never learned about logic gates in college or high school, this is a nice little book to show exactly what each kind of gate is. So a logic gate, we don't care about this one, so I'm going to brush past that. This one here is called a NOT gate. Okay, so it means when the button is not pressed, the light is on, right? You could think of this as the input. When the input is 0, the output is 1. Okay, but when the input is 1, so when this is actually pressed, then this is 0, right? So if this guy's going to press the button and then it turns off because it's a not gate. So it should not be turned on. This was an OR gate. So it means that one or the other button should be pressed. And also both is fine too, right? And then if both of them are pressed, if one or the other is pressed, then what you have is the light will come on. So the output will be 1. This is an AND gate. So both have to be pressed in order for the output to be 1 for the light to turn on. And here's an XOR function, which means that one or the other, but not both, need to be turned on. So notice how when they're both turned, when both the buttons are pressed, when the inputs of both is 1, then the button, the light is turned on when one or the other is pressed. But when both of them are pressed, the output or the light is turned on or 1, right? Okay, so again, I got a little ahead of myself, but why are we talking about logic gates? If you recall from the first wave of cognitive science, we talked about primitive operations. Primitive operations are just simple ways in which to compute things. So the logic gates themselves, these logic gates, are kind of ways in which you can get these primitive operations. And when you combine these primitive operations, these gates, right? When you combine them, you can get complexity that emerges out of just simple logic gates. So, in a sense, what we've done is if it's possible to use these logic gates in a neural network to implement these logic gates via a neural network. And then when you do that, uh, all those logic gates kind of combined, and then complexity emerges out of those simple operations. Okay. So to first talk about this, I want to talk about Boolean functions. And Boolean function is just a mapping function. Okay. It just maps a true or false input to a true or false output. And a Boolean function is the simplest building block of all computation. And neural networks are powerful because each neuron or node can behave like a flexible logic gate. And when, as I said, when you connect all these gates together, you get a network that can compute a bunch of things, from simple things like an AND or an OR gate, but you could also simulate things like face recognition or object discrimination. Uh, it's pretty flexible, and it's kind of crazy how it works, but it does. So you get these simple nonlinear functions, these Boolean nonlinear functions, and when they combine together, you get complexity that emerges out of that. Okay, and so yes, a Boolean function is there's like this input, right? Let's say an event. Let's say event A. An event A occurs as input to this node, and then this node is either true or false. Okay. So again, I know that this doesn't quite make sense yet. I'm going to talk about Boolean functions and different types of gates, but just know that I'm going to connect it back to neural networks when I'm done. So we can do a not function. A not function, as we showed in that book, right? A not function is basically you output true if the input is false. So if the input is false, that's analogous to not pressing that button. So when you don't press the button, the input is false. Therefore, the output is true, meaning that the light is turned on in a sense. Okay. And so you can say, so notice how when when the input is false, the output is true. But when the input is true, the output is false. Okay, that's essentially what a NOT gate is. And then we can talk about multiple events occurring, right? So multiple inputs go into this node and output a true or false. And when I say that this node is either true or false, that's analogous to whether the neuron or the node will fire or not, right? So this is the input from other neurons that feed into this neuron and tell it whether to fire or not. So that's kind of what I'm getting at here. And you can simulate different logic gates with a neural network. So here is with two events. So if you have two inputs, right, you have uh, notice how we could simulate an AND function. And an AND function is when the output is true if both inputs are true, and only if both inputs are true, right? And so you can think of this as, we can think of this in a logical sense. Like if the street light is green and there's nobody in front of me, then I can press on the gas, right, and go through the intersection. That would be like an and function. Or you could say, if my boyfriend gives me chocolate and flowers, then I'll kiss him. Okay. That would be like an and function. But notice how if your boyfriend brings you just chocolate or just flowers, you're not going to kiss him, right? That's sort of the idea. So notice how if events A and B are false, then the output function or the output is false. If event B is true, but event A is false, then the output is also false. Finally, if event A is true and event B is false, again, it's false because both events need to occur at the same time. And it's only when A and B are true is the output false. That's basically what an AND gate is. We can talk about an OR gate or an OR Boolean function. And in here, the idea is that one event or the other need to be true. Both of them can also be true. So just at least one or the other, but also both can be true. If both of them are true, then the function is true. So notice here, when both A and B are false, the function is false, the output is false. If event B is true and event A is false, then the output is true because A or B need to be true, which in this case that satisfies that. Now, if A is true and B is false, it's also true because A or B, right? And then finally, if both are true, then the function is also true, right? You can think of this as if my boyfriend gives me chocolates or flowers, then I'll kiss him, right? But if he gives both, that works too. And then we can talk about an XOR function, and an XOR function is only true if one of the inputs is true, right? And if only one of the inputs is true, right? So here we have if A and B are both false, of course, the output is false. If B is true, but A is false, that's good. That means A or B exclusive, right? Exclusively A or B. So then the function would be true. If event A is true and then event B is false, then the function or the output is true. But if both A and B are true, then the output is false. Okay. All right. So I know this is a little abstract at this point, and you're probably thinking, I'm not quite sure why we're talking about this. Hopefully this will be a little bit better. Okay. So imagine if this is our receiving node or receiving neuron, and our receiving neuron is getting activation from input one or neuron one, and neuron 2 or input 2, right? And so if you wanted to simulate an AND gate or an AND Boolean function using a neural network, right? You can do this, right? I'm going to do it now for you. So again, this is the truth table for the AND function. So we say if both are false, then of course the output is false. If 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 input 2 is true but input 1 is false, then the output is false. If input 1 is true and input 2 is false, then the function is false. And only when both input 1 and input 2 are true is the output true, right? So how do we do this? Well, we convert these true and false the trues and the falses. We convert them to zeros and ones. Okay, that makes it mathematically tractable. So we multiply the input by the weight, just as we saw before. And you do this for both inputs. Okay, so if the input is 0, 0, so input 0 times weight 1, that's 0, plus input 2, which is 0, times 1 is 0, equals 0. So then that means that this neuron, because 0 is less than 2, this neuron would not fire because the threshold is 2, and so the activation of this neuron must be 2 or greater in order for it to fire. Okay, and we can do this, you can do this math with, so if it's input 2 is true, but input 1 is false, you find that the activation is 1. Same with if input 1 is true or 1 and input 2 is 0, then again, the activation will be 1, so it won't fire. And only when the input 1 and input 2 are both 1 does this fire. Why? Because input 1 is 1, so input 1 times weight, which is 1, plus input 2 times weight 2 is 1 times 1. So it's 1 times 1 plus 1 times 1 equals 2. And so, so it would fire. Okay. And then in the next video, we're going to talk about Hebbian learning and the perceptron convergence rule.